So now we will see the expression for the power transmitted by belt drive. As we know, in a belt drive, the driving pulley pulls the belt from one side and release the belt to the another side. From where the belt is being pulled, that side is called as a tight side, and from where the belt is released, that side is called as a slack side. Now suppose let T1 and T2 is the tension in the tight side and the slack side of the belt respectively, and this tension is given in Newton. Similarly, R1 and R2 is nothing but the radii of the driver pulley and the driven pulley, which we many times we call as a follower. So from this we come to know that in the belt drive there are two tensions or two forces. One is called as a forces at the tight side, and another is called as a force at the slack side, that is T1 and T2. And this T1 minus T2, this is the force which is responsible for the rotation of the belt drive. Because of this the rotation of the belt drive occurs. Now V is the velocity of the belt in meter per second. This velocity in the belt V is, we know, is given as pi dn by 60, where d is the diameter of the pulley and n is the rpm of the pulley by which it is rotating. Thus work done per second is given as T1 minus T2 into V, Newton meter per second. T1 minus T2 into V, Newton meter per second. As work done per second is nothing but a power transmitted, and that's why the power transmitted P is equal to T1 minus T2 into V. Power transmitted P is equal to T1 minus T2 into V watts. As we know, 1 Newton meter per second is equal to 1 watt, right? So from this we can easily consider that the torque exerted on the driving pulley is equal to T1 minus T2, that is the forces multiplied by R1, radius of the driver pulley, and the torque exerted on the driven pulley is equal to T1 minus T2 into R2. Now look at we will look at another expression that is called as a ratio of the driving tensions for the flat drives. As we know, if we consider one pulley and these are the two, this is the belt, and this belt is making an angle of theta, which generally we call as angle of lack or angle of contact to the pulley, and one side is a T1, another side is a T2. So expression for the ratio of the driving tension is nothing but T2 and T1 and T2 are the driving tensions. Its ratio T1 minus T2 is equal to e to the power mu theta, or in terms of log to the base 10 this expression is given as 2.3 log to the base 10 T1 by T2 is equal to mu theta. Okay, so where T1 is nothing but a tension in the belt on the tight side, and T2 is the tension in the belt on the slack side. But what is the theta? Theta is the angle of contact in the radians. Just look at this angle of contact in radians. This particular angle theta is not in degrees, but it is radian. That thing we have to remember. And mu is a coefficient of friction between the belt and the pulley. Mu is coefficient of friction between the belt and the pulleys. So we can say from this expression that is ratio T1 by T2 is a function of coefficient of friction between the belt and the pulley and the angle of contact, or we can say angle of lap. So generally what happened, whenever we consider a belt drive, generally the angle of contact is small in a smaller pulley, and that's why generally whatever the power transmission capacity of the belt drive is there, that is decided by the angle of contact at the smaller pulleys. So generally this theta is considered at the smaller pulley. Now another expression we will see, that is determination of angle of contact. How to find out the angle of contact for the open belt drive as well as for the cross belt drive. So for open belt drive, this angle of contact theta is equal to 180 minus 2 alpha. This angle of contact theta is equal to 180 degree minus 2 alpha multiplied by pi by 180 degree radian. And for cross belt drive, this angle of contact theta is equal to 180 degree plus 2 alpha multiplied by pi by 180 radian. So this is the expression for the angle of contact. Now whatever the formulas we have to we have seen, we will summarize it. For open belt drive, and for cross belt drive. For open belt drive, we have seen the first expression, that is length of belt L is equal to pi by 2 d1 plus d2 plus 2x plus d1 minus d2 square divided by 4x. And for cross belt drive, length of belt L is equal to pi by 2 d1 plus d2 plus 2x plus d1 plus d2 square divided by 4x. Similarly, the power transmitted, the second expression which we have seen, that is the power transmitted by the belt drive, and this power transmitted by the belt drive is given as P is equal to T1 minus T2 into V. Similarly, for the cross belt drive, this expression remains same, that is P is equal to T1 minus T2 into velocity V. We know velocity V is equal to pi dn by 60. Velocity V is equal to, for the cross belt drive, same, pi dn by 60. Then ratio of the driving tension to the ratio of the driving tensions, that is T1 divided by T2 for open belt drive is equal to e to the power mu theta. Similarly, it will remain same for the cross belt drive also, that is T1 by T2 is equal to e to the power mu theta. And the fifth expression which we have seen, that is the determination of angle of contact for the cross open belt drive, this theta is equal to 180 degree minus 2 alpha pi by 180 radian. And for cross belt drive, this expression changes, that is theta is equal to 180 degree plus 2 alpha into pi by 180 degree radian. Now from where we can find out this alpha? Alpha is equal to, for the open belt drive, this is R1 minus R2 divided by X, and for cross belt drive, this alpha is equal to R1 plus R2 divided by X. This alpha, this we have to see as a sine alpha. This is a sine alpha. Many times we can neglect this sine. So these particulars, when we consider sine alpha, this will this alpha, if we use a sine alpha, the angle comes in degree, and if we just assume alpha neglecting sign r1 minus r2 divided by x, then this expression will be in the radian. So this thing we have to remember, r1 plus r2 divided by x.